Hey, welcome back to the stream. This is a bit late if you're in my time zone, perhaps. It's like 8:30 p.m. on Friday. But I was doing some work off stream on some of the robot features, like the LEDs. In this stream, I just wanted to spend some time just going back into the disassembly of the Gimbal firmware to try to look for the right gain parameters we could tweak to hopefully give this gimbal more of a chance of operating in its stable region when it's pointed further down. So this whole project is getting much closer to being something I can run in a more autonomous fashion. So I've actually had it streaming pretty much all day today. Switch to that view here. That's Tuco destroying some cardboard as he does. Here's the debug view. Let's see. That's pretty close to what you've been seeing over on Twitch. So this project has its own Twitch account over at twitch.tv/TucoFlyer. And some of the stuff I was doing recently on the software was to integrate the status of the recording and streaming with the remote control and the web interface and the LEDs and all that. Oh, Tuco's over here joining me now. I can find the robot over here. So one of the big, whoa, I do need to pay a little bit of attention when flying it around manually, because it doesn't have any sensors yet for avoiding obstacles. So that's all on me now. That's one of the big things to do before I can actually get this thing completely hooked up to chat and computer vision controls. Oh yeah, hey robot. We're just like right over here. So yeah, the robot itself has infrared sensors for detecting obstacles nearby, and those are not really hooked up in software yet. So one of the near features to think about implementing is to include software support for those infrared sensors to detect the height of the robot and to detect nearby obstacles. So that kind of stuff will be really useful in the near future. So I think some of the future streams are going to focus on doing some of the math to get a good height estimate using the IMU. So like we already have an angle estimate for the whole robot. So combining that with the distances from the LiDAR sensors will give us the overall height of the robot, which will be useful. But yeah, right now I'm thinking about the gimbal, and so the gimbal is fairly stable at the moment. We now have the ability to detect when the gimbal is unstable, so I can do that manually. For example, let's say I go downstairs. Oh, cool. Yeah, nice to see you, Bill. Yeah, and if you're around, yeah, I'd like to get some coffee. That'd be nice. So I don't know if you can hear that. I'm letting the gimbal. Oh, yeah. So it buzzes. But we're actually automatically detecting that now and aiming the gimbal back up toward its origin location if it becomes unstable. So normally the gimbal is pretty much free to move, but if I just inch it down there, so if yep, right there, so this oscillation just builds up in the gimbal, and then it won't really die down until you get it into a different mechanical position. So there's a control loop in there now which monitors the gimbal motor current, and if either the oscillation or the peak motor current goes out of range, then we can first start by rehoming the gimbal, pointing it toward its neutral location. And if that doesn't solve the problem within, I think, something like 4 seconds, we can power off the gimbal motors. So that's where we're at right now. So the basic ability to recover from and notice gimbal errors and just like log that data, so all that's in place now. And also, since fixing the LED, there was like a firmware bug actually that was preventing the LEDs from animating correctly. And since fixing that, I added a little bit of LED animation. Let me turn on the DSLR and we can see that. Yeah, as always, the camera needs a card. The ritual of feeding the camera cards. So William is asking about the noise, the vibration, something grinding inside. Which noise are you talking about? I assume not the camera noise, but do you mean like the lower pitch noise the winches have been making lately? Because that's actually something I've programmed in there intentionally in an effort to overcome static friction. Oh, the gimbal noise, right. Yeah, no, so the noise you're hearing is actually a symptom of an oscillation. I don't know exactly where the oscillation is because there are many layers of control loops all stacked on top of each other here. And so any one of those could be the root cause of the oscillation. Let's see, how far have I narrowed it down? So I don't think the oscillation is in... I don't think the oscillation's in the current... So there are a bunch of layers of feedback loops in the motor controller. At the lowest level, there's like the pulse width modulator. Then there's a current feedback loop that tries to achieve a particular current as measured by the A to D controller, or A to D converter by measuring, or sorry, I'm misspeaking all over the place tonight. There's a control loop that changes the pulse width modulator duty cycle of the motor windings in order to achieve a particular current level. And so that's like the lowest level, and then above that there's a level that tries to achieve a particular velocity by modulating the current into the motor. And then above that, there's a bit of a question mark, and that's what we're going to be getting into in the reverse engineering tonight. Oh, Colin, is that a Discord for OBS? That's cool. I'm actually really terrible at like engaging with open source development communities, but yeah, I should probably engage with OBS more because I've ended up reading a bunch of the source code, and I enjoy how I can write a plugin for OBS instead of reinventing all of the wheels. So that's been fun. Oh no. Oh yeah, Tuke's like way over there. Where is he? Oh, he's way over there. This is gonna make it hard to film the active part of the gimbal. There he is. Does he want more food, or is he just trying to figure out what my recycling is doing? Alright, so here's the robot itself up in the DSLR window. You can see it's like a quadcopter gimbal with some 3D printed adapter parts and some extra heat sinks. And then the body of the robot. Some sensors we haven't mostly written code for yet. And there's Tuco. So I was going to try to demonstrate the LEDs up here. Maybe I can aim it over in this direction. You can see. Yeah, so you can roughly tell where it's aiming now. So the idea is that double flash indicates that it's streaming, and the single flash indicates that it's also recording locally. I can also change the status with the controller now. So I could, for example, do this. I need to make a diagram for all the controls for this thing. There's a logic that makes sense in my head, but it's a little bit awkward to describe. But I could turn off the local recording, for example. And so now you see it's got the double flash, so it's still streaming on Twitch. I could also turn off the Twitch stream, but I won't because the Twitch stream is fun. I can turn the local recording back on. So it should start back up. Hello, local streaming. Oh, there it goes. I don't know why it didn't work the first time. But yeah, now I mean, it's good feedback though. Like if the streaming is being flaky for whatever reason, like I don't really have good error propagation right now. It's effectively taking the event and moving it through this Rube Goldberg machine that eventually lands in the same event as effectively like poking the start or stop button in the Qt OBS UI over here. Where is Tuco? I was gonna try to actually get the cat camera doing the cat camera thing. But yeah, the flashing is kind of nice. That's like more what I wanted for kind of warning bystanders that this thing is streaming and giving myself a way of noticing when UI changes take effect. It goes over here somewhere. Hey, Took. Oh man, this cat. Oh, that was an end stop. That was part of the problem with the current very naive motion control system is that the gimbal does not rotate 360 degrees. It rotates most of the way around, but it does have an end stop. And so I imagine there being kind of a feedback loop that influences the location of the flyer within the room based on where the gimbal is near its end stops, and that would be how I avoid this problem in the future. But right now it's in kind of a suboptimal location, so I've got to move the robot, which doesn't happen automatically. I've got to use the controls here. You can tell it's kind of shaky right now. That's really because the controls are extremely simplistic in the software right now. So I'm hoping I can improve the stability with software. If not, there are a bunch of hardware changes I could make. Right now the camera is on this long kind of pendulum boom in order to give it some additional reach below the level of all the furniture in the room, so that the cords can kind of stay relatively high, and then the camera drops below that by up to ½ a meter. That's the idea behind it. I can adjust it if it's too much, but my hope is that if the software is smart enough, it can either move it smoothly enough or maybe actively compensate for the pendulum motion such that that's not really a problem. Oh yeah, no, that's a great suggestion. No, Bill is suggesting Bill from AT Makers is suggesting like navigation lights, and yeah, Bill's saying that they recognize the colors red and green for a port and starboard, and then white for center from boats. And yeah, I'm also slightly familiar with that kind of navigation coloring from like remote control aircraft, and that would be useful for sure. Right now, the kinds of navigation that have made the most sense are related to where the camera is pointed and then kind of winch relative motions. So yeah, my original idea for the LEDs on the top of the flyer were actually more of that sort of navigation light, kind of a static color per direction. But what I've got it doing right now is actually just mirroring the status of the winches themselves, which seem to be a useful thing for them to do, at least. Let me bring it closer and maybe illustrate that point. Oh, I'm gonna hit the microphone. Oops. Usually I wouldn't bring it this low. I was just going to try to get the top of the flyer somewhere I can see it with the DSLR. Hey flyer, usually you don't see the floor. Oh man, the pit loop is full. Yeah, that's okay. Let me just get the DSLR on the top. Show you the thing I was going to show. So the LEDs at the bottom, you've seen those. This stuff at the top previously didn't have much to do. My original vision for this was that it would be some kind of navigation light that would be visible either from like a mini-map camera or from humans up on the upper level balcony of this place in the like living area rather than the work area. But I didn't really have a clear idea for that. And right now I just have them all actually connected to display the same kind of LED pattern that the winch on the corresponding cord is displaying. So, can I get these things to do anything useful? I was going to try to get it out of the force range to display a different LED pattern, but I don't think it's going to do. If I move, you can see it, but then it's hard to get on camera. Oh. Don't want to hit the camera on the chair. Okay, now there's actually a gray error pattern showing on these LEDs, but you can't see because it's off the camera. Yeah, so like that. You can see the errors at least. So it is actually kind of useful because just given how spread out the actual winches are in the shop, it's a little bit nice to have the error codes and the motion displayed somewhere kind of close together like this. Yeah. Retract. Oh, Tuke's down here. Alright, so I mean that's like kind of a summary of what we've got. We've got some LED patterns. We've got that automatic recovery behavior so that if the gimbal is oscillating or the motors are stuck, then we'll try to rehome it, and if that fails or is taking too long, then we'll just cut the power to the motors. So that's all working pretty well. But there's still that stability problem in the first place, that if I actually try to aim it down, then eventually the buzz happens and it just triggers that problem where it's no longer stable. Mechanically, the gimbal should be able to aim all the way down. So it seems like maybe there's some kind of gain adjustment we can make, or maybe a filtering adjustment. So anyway, that's the background, and I think that's just going to segue into spending the rest of this Friday night trolling through disassembly in IDA to try to find the exact gain parameters that might matter here. And I've got some IPA here. I think we're done with the physical world. Put this DSLR away and get the IDA out. I cleaned my desk, isn't it so clean? Yeah, I wouldn't have cleaned it at all if I wasn't actually trying to use it to take photos. Oh. Oh, cool. Greg on YouTube chat says they can't wait to see it complete. They've been watching for a while, and it's been interesting to see the progress. Yeah, it does seem like it's getting close, isn't it? I mean, there's like the long tail of minor changes. I think as far as major stuff goes, making it actually interactive over the internet is a big milestone. One of the big prerequisites there is the automatic collision avoidance, because right now it's actually pretty safe to let random people drive the gimbal. So like actually we could have gimbal controls from chat pretty much any time now. But before I would let either the computer vision or the chat bot drive the winches, I want them to have collision avoidance features that they don't yet have. Oh yeah, Roger suggests a thermal camera. Yeah, that's totally on the menu. There's sort of the bot proper, the flyer itself, and then there's been this kind of, so far, hypothetical menagerie of extra robots that we could add to this equation. So some kind of ground level robot that could chuck bolts for Tuco, some additional things that can clamp on to the balcony of this place and look down. And so I think something in that category would probably have an IR sensor. There are a couple of IR cameras around here that we could maybe repurpose for that kind of thing. All right, I think we should head back into IDA. That was enough demoing. So this will be in microcontroller 2 and that final joint. Oh yeah, I'm gonna have all these great graphs up here. I know this isn't IDA. Do I need to reload this? Yeah, so these are our inputs, message bus, rates. You can even see the streaming output. Anyway, we don't need that right now. Oh man, I need to implement that additional hysteresis in the winches. There's also something that goes wrong when the motion of the robot itself gets really jerky. Something additionally then goes wrong in the gimbal stabilization, which I haven't taken a look at. I don't know whether it's something in my code or something in the gimbal firmware. Obviously the preference is to avoid jerking around the gimbal in the first place, but then maybe there's something else we can do to fix it also. Alright, I'm going to open my ancient version of IDA again. Oh yeah, and there are a couple of places to play along at home. There's the TucoFlyer repository on GitHub. Not Gotham, that would be cool. I always wanted to be GotHub. Alright, bot controller. Yeah, so if you go to TucoFlyer, this is the organization for this whole project on GitHub. And there's CAD models, there's software, there's firmware, there's OBS stuff. Most of the work has been going into this bot controller, which is mostly written in Rust. And it has some web templates, including some pages about the internals of the gimbal, which are annotated to explain the RAM offsets in there. So this is actually one of the places we've been storing the results of our reverse engineering. If you go to this gimbal internals.jsx, this is used to generate this page, which I'm not logged in right now, so I can't write to any of these values, but you can at least see the annotations. So this shows you values in that parameter space, which is those, it's that set of 128 16-bit values. It's actually a little bit different from that because they don't really bounds check it, but this is like the useful expanse of it, is from 0 to 7F hex. They helpfully end it with the firmware version, so if I was logged in, I could request that we pull that, but right now I'm only seeing the stuff that's being incidentally pulled. And that's what we know about it via reverse engineering so far. And the red parameters are the parameters that are being sent outward. So in this case, these are the commands we're sending to the gimbal to help it track whatever we want it to track. We get back some motor status, this current measurement, which we use for error detection. So we could even graph that from here without any special privileges. Isn't that nice? I also recently added this thing so you can see how long the gimbal's been in some kind of error state. So if I manually were to push it down, eventually it starts buzzing, we detect it, and when it gets above a threshold, then we try to rehome the gimbal. Similar thing happens with the peak current, so if it's actually stuck against something, then this will detect that. Anyway, oh, there's one other thing in that area. So, you know, that's pretty good as far as detecting this problem, but ideally you want to prevent it in the first place, extend the range of stable poses that this thing can be in. So there was something gain-like that we found, which I was then skeptical about. Oh man, that spool pig. There's an extra hysteresis I need to add to the firmware, which I've been, it's like on the to-do list, but I've been kind of putting it off. I looked at this and I don't think it is anything. I should just annotate that it probably isn't anything. So this is the one that we looked at that seemed like I could use it kind of like a gain. But then I looked at it more closely, and it seems like it might be just some kind of unit conversion. So this seemed like it goes between the gyroscope and parameter 4, which, if you look up here, it's explained as a gyro angular velocity. So I think it might be useful to understand the pipeline of control loops here between that point and the motor controller. And we know some things about the motor controller from the factory calibration modes. So param 18, that's a mode which we've been experimenting with. We spent like a whole stream looking at places where that mode was being used and trying to figure out what it meant, and then just trying it out. And it turns out that there are these two different layers of the control loop. There's this low-level layer, which is entirely contained within SysTick, the SysTick IRQ. And that just seems to be about currents, like maintaining currents in motor windings and rotating those currents into a particular coordinate system, that kind of thing. And then there's a feedback loop on top of that in timer 2, which seems to be about the motor velocity. But I don't know how that whole thing is then connected back to the feedback in param 4, for example. And I know it's using param 8 at some point as an accumulator, but I haven't looked closely at how that actually works, or what kind of gains might be involved. So that's kind of what I want to get into. I'm going to get some tea. I'll be right back. Matt is asking if I've had any contributions from other people on GitHub yet. I have a little bit. We've been collaborating a bit on the chat part of the project, but no, so far I've been the only one working on like the parts that I started here. So yeah, like the Tuco chat stuff has been Morix so far. Is that how you say your name? Sorry if I'm pronouncing it wrong. And then the CAD and the firmware and all that has just been me so far. Which seems like about right. I mean, it's like difficult to collaborate on stuff that's firmware for a robot that I have here, right? I'll be right back. I know other parts of the country are experiencing actual blizzards right now. It still feels cold here when the wind just blows straight through the shop. John on YouTube chat says sometimes the threshold needs to be dynamic. I don't know what threshold you're talking about, but sure, probably. There are a lot of just like stacked up control loops here that still need to be optimized. Yeah, I mean, so like the code I'm putting here is not so much necessarily an invitation to collaboration as it is a way for people to learn from what I've done and maybe steal from it. So like it's not something where I'm going to expect like, oh yeah, I built one of these exactly like it and I'd like you to take this change. But it's more like I expect people to learn from what I've done and maybe make their own thing that includes a bunch of pieces from here, or maybe even just like learn from some of the code or some of the CAD designs. You know, it's not something where like I expect that this exact prototype is going to be something that people want to build on so much as something people want to learn from and replace. Because it is a prototype. It isn't like enterprise grade robot for cat. It is prototype robot for cat, right? So anyway, that's the Tucofly repo. I've also got scanlime/FY Gimbal, which has some more info about the actual Gimbal protocol. You will not find the actual databases in here, but you will find binary patches and mapping files. So you can find addresses for stuff that I found in the firmware, also train. And you can find scripts that I use to apply patches to the firmware, which like jump over loops that I'm not using, for example. So yeah, here for example, I'm writing to param3, which is one of these. I'm writing to param3 on the PC side, and the third microcontroller, the one that actually manages the IMU, it's effectively writing to param4. But somehow that turns into some kind of integrated thing in param8, I think. And then to some motor controller parameters that we can't see in here. So I think actually the first place I want to start is looking at what happens in the other motor control modes that we do understand, and look at who else is writing to that same value that we know is velocity. Because that's like the highest level part of the motor controller that we actually know so far, I think. There's some stuff we kind of fuzzily know, but that parameter, I know that is velocity. I also know that just leaving that web page open will heat up this Mac. I've got a temperature sensor on this Mac in the rack, and it will heat it up. Mr. Radar says in Minnesota they're having unusually warm weather because it's gotten above freezing every day that week, or this week. That's great. Yeah, I know I'm a wuss complaining about the weather in California, but you know, I also live in a drafty warehouse. I don't have like a warm box. A lot of people live in a warm box, and I think that's a cool idea. I just don't have one of those here. Bing bong. All right. Where do we want to start here? So param 18 maybe. I feel like I'm diving in under something deep. So motor mode. We want something that works in that velocity motor mode, which is... I have to open my notes now. Oh yeah, and I don't even know what param 1D and 1E are. I assume there may be an acceleration limit, but I don't have any idea really. Okay, yeah, actually this is quicker. We can just param 50 is going to end up copied to the velocity. There we go, time to motor velocity command. So who else writes to this thing? And where are we right now? This is in motor enabler disable in current mode. Which that's gotta be a terrible name for this. Can we give this a better name? This is like a mode-specific tick function. Okay, I'll call this motor mode-specific tick. Alright, so this is useful for understanding what these values mean, but the behavior I'm interested in is what happens in the motor's normal mode, which is mode 1. So that's interesting. That actually bypasses setting time to motor velocity command here. It sets this debug enum, which as far as I know doesn't mean anything, or isn't useful in this firmware build. Does seem like that's the input we're looking for. But we only end up on this path in either modes 5 or 3, which are not normal modes. So who else writes to this? It's just that and time to body. Oh, this is it. Okay, we can give this a better name. This should be named something like normal velocity command. Or like motor. Motor normal mode velocity command, I think. Oh, cool. And this is this is just written to at the end of this nice big time for body function. That's cool. No, it's not that big. Let's assign extend and add. Oh yeah, huh. It's a combination of R0 and whatever's in here. I'm gonna have to assume this is a velocity integrator. And then I'm gonna have to check that. Yeah. Velocity command integrator. A lot of hard-coded. These are thresholds at least, but. So I have a few paths here. There's a loop. No, that's just a bunch of downward arrows clustering together right there. Yeah, alright. I remember looking at this and being depressed by how few coefficients it seemed to have. I was hoping it would be multiplying by stuff from parameter space, and this clears the integrator if we don't have this this command 0 stabilization enabled, which I think is actually some enable flag for like the whole IMU stabilization subsystem or something. This is like a reset. I mean, it's just random detail. This stuff up here is the follow loop, which I'm ignoring. This basic block is like the first interesting part of this function to me right now. That's what it's adding to the accumulator? 2FC. Is that an acceleration? So yeah, I was seeing that moved. So it's I don't know why we'd be taking the absolute value of the acceleration value if that's what that is. That's the integrator, and R12 is the additional thing we're sticking in the integrator, this tick. It's either R0 or R7. That's the 0 path. That's some kind of mode for this. Yeah, maybe that isn't what I thought it was. Rotating param 8, which is that accumulator that is probably important here. Oh, R1 is the stabilizer input. And then there's the offset in param 4B. Is that right? For param 8, which path are we on? Like, I don't know what this flag represents. This might be like a reset path. Because usually param 8 is something that has feedback on itself. I wouldn't expect it to be calculated like this. Yeah, on this path we're loading param 8 and adding to it. That's the reset path, and this is the normal path. Oh, that's the offset in R2. And the stabilizer input in param 9. Do we know how param 9 is calculated yet? Gimbal. So we just note this is something from MCU2. We might already have the gain applied for all we know. And then this was the thing that kind of behaved like a gain, however. And it only affected param 4. Oh, I just noticed Bill's question. If you have a second, can you explain the address ending in 2FO? Are those multiple labels for the same address? that have been? These are totally not in that range. So I don't know exactly what address you're talking about, but as for multiple copies of this, this is just by convention. This is like, imagine this is like a spreadsheet, and this is a column that indicates what address we're at for that line. So we end up with the same label for these lines because no bytes have elapsed between those lines. So it's only until like we actually emit some bytes that we end up 2 bytes later at the next address here. The other thing I can think of that might be related to your question is stuff like this, where there's a dash, and that is actually representing a subtraction. It's actually a notation that you might use to write this in an assembler, but it's not representing a subtraction that happens in the processor, if that makes sense. It's just notation. This indicates that the address you see here, I mean, you can change how this is represented. For example, the instruction is actually just take R4, add 96 to it in hex, and then look at the memory represented by that. That's what the brackets are. It's dereferencing memory. And then load that into R2. But it's helpful in the disassembler to note that this is actually a base address. We can tell the disassembler that this is, oh, why do we get that as checksum? Anyway, like these are just the same things, right? These names are just shortcuts for numbers. And so this is just indicating that what we're actually doing here is assuming that R4 already has the value of param 0 checksum, which is the same as 3D8. This calculation is the offset from where we already are up to where we want to be, which is this offset for param 8. So it's just kind of spelling that out in this way, which directly relates to how you would actually write that in the instruction encoding. I don't know if either of those were actually what you were asking about. Yeah, feel free to ask assembly language questions. I mean, I know a lot of folks don't work with assembly language day to day, so yeah, if this stuff is weird, just like ask me what it's about. Oh, yeah. Okay, so Bill's asking about the base address. So many of these have the same thing after the minus. Yeah, exactly. So that isn't actually part of any real address or anything. That's the value that we're assuming is resident in R4 at this point. So right here, the reason all of these say like 3D8 here for R4 is that we know as reverse engineers that R4 contains this value because we've deduced that the compiler intended that value to be in R4. And we can find that by tracing back up here and just finding where R4 was written to last. Where was that? Whoa. That's not how you do it, kids. Oh yeah, it was like way up here. So R4 for the length of the entire function has been a base address for the parameter space, which is also known as 3D8. So all of these we can write like this. So the actual encoding will be an offset from 3D8. And that's really just because in ARM there aren't enough bits to write that entire address. So like this instruction is only 16 bits. You don't have enough bits for this entire 32-bit address here. In fact, this instruction doesn't even have enough bits for that because this whole instruction is only 32 bits. So this instruction, in fact, encodes an offset to some other part of flash memory. a literal pool where you can find this value. And that's all being simplified away by the disassembler already. So this sequence of bytes is like, go fetch a value from down there. And IDA, as a disassembler, is noticing, okay, down there in the literal pool was actually this value equal to param0 checksum. And I can, oh, there it is, Q. Yeah, so I can represent this as a 32-bit value. I can also, if I go to the disassembly, where's this actually coming from? So the nearest literal pool may be behind you. It's probably down here, actually. Right there. That's the actual value. IDA makes it a little bit clunky to actually get to this value because usually you don't care about the literal pool, but so the instruction itself points to this value, which then loads it into R4. Yeah, and you just don't want to do that super often, so you tend to do that maybe once per function if you can get away with it in ARM. So the compiler will emit this sequence, or like this sequence, to load that value that was way down there into R4, and then just keep it in R4 as long as it can. So down here, it can use only 2 bytes, plus the value that's already in R4, to get this other variable loaded into R0. So it's actually pretty efficient. It means that you can, you can have large 32-bit or larger memory spaces, but usually work in terms of offsets. You'll see something very similar if you look at x86 assembly or pretty much any kind of modern assembly for a 32-bit system, or 64-bit. It's similar in 64-bit. So yeah, a lot of these numbers are offsets. Some of these are floating point numbers. So yeah, stabilizer input might already be in whatever velocity unit we're talking about. In which case, maybe the only relevant gains are on MCU2. I just don't see any accesses to parameter space that are interesting down here. Param 8 is an accumulator. With wraparound, right? Yeah. Yeah, param 8 is some kind of angular target. This is in units of hundredths of a degree. Between plus and minus 18,000. Can we see that? I forget how much this updates with the follow loop off. I'm still logged out. Oh, right. That is conspicuously at 0 for the roll axis. I wonder if it would be useful to look at the roll axis, like it might be simpler. I think the primate accumulator is mostly there for the benefit of the yaw axis, but I mean, we're looking at the code for the pitch axis right now. I have to wait for the yaw axis to rescale. This has gotta be follow loop related. So param8 only gets written to kind of sporadically. What actually goes into that parameter we care about? Okay, motor normal mode velocity command. It'd be great if we could just attach graphs to any part of this function. So the first fork in the road here is whether we care about the velocity command integrator here, which is just what I've chosen to name this, or that other fork, which seems to be the return value of this, like one of these several blocks of code. There's a 0, there's a negative constant. And then there's something which would, again, be the same command integrators who get 2 copies of this. Oh gosh. Wait, I need to check that. Is it actually doing compare and branch, if not 0, against param3? Which would mean it has different branch paths for whether we're commanding a motion or not, which is... I can imagine why it's doing that, I just was hoping it wouldn't. So this is param3. Oh yeah, param3. That's interesting. We're subtracting param3 and the motor velocity command integrator. Like that's a filtered version of param3 somehow. That's from the follow loop. Where's the gain? I was hoping to find a gain knob. Oh, cool. We got a couple of assembly questions. Well, Eddie says they're learning assembly in a class right now with the AVR instruction set. And then Concrete asks what platform I learned assembly language on. Well, that would be x86, because that's what I had. Yeah, 16-bit x86 was my assembly language tutorial. I think that this is all already in whatever unit it's in. I don't see any multiplication. Yeah, maybe I should approach this from a different side. I mean, I think this motor velocity thing comes somewhat directly via this combination of Pram 8 and Pram 3. How does Pram 9 figure into it? I think this might be something that's trying to be smart about, like doing some kind of hold sort of stabilization when we're not commanding the gimbal to move and otherwise letting the motion dominate. But I don't think it's actually working correctly the way we're using the gimbal right now. And I don't think it matters that much, because we've got our own control loop that does that, but like with, like I don't know what part of that this is supposed to implement, but I don't think it's necessary at this point. Like, I don't think Pram 8 is working in a useful way. But we do have Pram 3 coming through. So Pram 3 is coming from us, and I think Pram 9 is coming from Command 0. Can we verify that really quick? Oh, it won't come from Command 0 and MCU2, because this is like the same microcontroller that would be sending Command 0. If we open a different micro, we should be able to see Pram 9 coming from Command 0. Or Command D on here. Hush pig. Can I modify the firmware to ignore the non-command path? I don't know what you mean. You mean, if I understand you right, I think that's already the part that I took out. I mean, I already removed basically all the code that, like jumped over the code that would have been responsible for adjusting the heading back toward the neutral position, so that I can replace that with my own code. And so that's that piece right there that manages Pram 8. Yeah, maybe I could remove some of it, but as far as I know, it's not having any effect. Oh yeah, 9 I had labeled as gyro angle, but I think that's actually a stabilizing input that comes in through Command 00. So yeah, we're writing it right there, Pram 9, and reading it out of this incoming packet. Which we haven't bothered annotating yet. But yeah, that's Command D, which is what microcontroller 0 gets after it's gone through this chain of microcontrollers playing telephone. is that? Yeah, that's offset 4. Alright, so where does that come from here? I should expect this to start crossing into the boundary where microcontroller 2 handles all the axes instead of just axis 2. Where do we go? Whoa. Huh. Yeah. These are the stabilizer outputs. So we've been here before. This is in the IMU. Does a bunch of transformations and then ends up with something that it writes out. Locally, it ends up kind of going through this and then ends up eventually sticking it in Param 9. Yeah, via this stabilizer out F32 local pitch. That's in float. Param 9 is in 32 or in 16. So that's what this conversion is for. Multiplies by 100, casts integer. But something similar happens to write these values into a packet which gets sent remotely. Really? My heart sank as soon as I saw that this was coming out of an ATAN too, because like where the scaling must have been past this. I wonder if I found all the, I don't know, maybe look at the gains, or values that could be gains in here. Oh, Cronkite was asking for more info on that first assembly project on x86. Well, I mean, it wasn't so much like a single project, so much as the thing that I was like really interested in learning, and um, yeah, I guess I didn't do like a single big project, but I just um, I worked through this book that had a lot of interesting examples and wrote just a lot of like throwaway little 16-bit programs like .com files, and wrote some TSRs and wrote some inline assembly. I don't think I wrote any like sizable program entirely in assembly, but it was just like, it's like useful to know how to write assembly, but you don't usually write entire programs in it. It's usually something you want to know how to read or write little amounts of these days. And even at the time I was learning it, I didn't really want to write entire programs in x86 assembly. It was more like I did some of that to learn it, but was then mostly writing inline assembly in my C programs. I did later on write programs entirely in assembly for PIC microcontrollers. The tool chain for those just didn't really have a C compiler it liked, so I would end up writing assembly pretty much all the time there. Yeah, I mean, I could, so Bill is suggesting I binary patch out all the code I don't understand, and I think that was a good way to take my one problem and give me two problems. So a lot of these are pretty round-ish numbers, it seems. The ones that are like inputs that don't change. It's for C updated. I don't think I care about the follow loop. It's not even turned on. Like, the pitch code is patched out right now. Oh, do I know what these are? These look like more IMU-related calibration parameters, and they're not documented. This is, so 62 is that one that right now comes closest to being a gain parameter for me. This is going from the gyro feedback to parameter 4, which I don't know the units of what parameter 4 is supposed to be. But it's possible that's the right place to adjust the gain. It just seems like there probably should be something better, but maybe that's it. I don't see a lot of other places for such a parameter to hide. But this, this being the same value for all the axes, I kind of figured that's maybe like a unit calibration issue. So, yeah, maybe the thing we should be going for next is figuring out what these parameters are. What's 55 through 58 doing here? Specifically 55 through 57 look like they might be pretty interesting. Main. What? So 5, 6, 7 are a single tuple here. Where are we? So this is in main, before the main loop. Kind of late though. Before the PC attach stuff, before we initialize the stabilization outputs. This is 8, 9, AB. So 9AB or gyro compensation. What is 8? Oh, right. I thought I wrote that down. That's the flag that indicates that the gyro drift compensation has been completed. Okay, so that's all gyro drift compensation stuff. So this is right after the gyro drift compensation. We do this other thing. Floating point multiplies by this number. By 1,000. Huh. This is, oh, the compiler. So this is just loading a 32-bit float, multiplying it by 1,000, but the pointer comes from way up there. So this is param 55. Six is in R7. And I think this is the next one. Huh. It's acting like this is 0, but I don't think it's 0. Why is this 0? No. So these are being considered for the gyro calibration. So we have these punctuated by a couple of other 32-bit values. Not much before that. Huh. I wonder what's in there. Where are you? These aren't dynamic values, are they? I assume these were static, but let's check that. Yeah, those are static. Whoa. Hitting a weird invisible wall there. Maybe my oscillation threshold is a little bit too... Yeah, actually maybe having all these pulled so frequently is causing my oscillation threshold to become a little bit too aggressive. Now I can go fine. Well, it's better fail safe than not, but that's annoying. I need a better metric there that isn't dependent on sampling frequency. Oh. It took... These don't look big enough to be gains. They might be offsets. This is per tick. Why are these values static? This is a filter. Looks like it. Oh, you're so cute, Tuco. Hey, fuzz boy. This is weird. So this is running per tick, but it has several exit paths which do something in a loop and then result in one of these three parameters being set. And so we end up setting one of these pre-parameters here. And then we capture them in the main loop. So there's a period where we run the stabilization for a while before like entering the main part of the main loop. There's a counter that ticks down. Are these used anywhere else? No. Does anyone else care about these values? So these might just be debug values that are like, by the way, here's some stuff that we did during initialization in case you care. But then otherwise it isn't used. Can we do any better than that? What with this cat? I don't see him. Oh, there he is. Got lost behind the coffee table again. Hey. Oh no, are we oscillating? Oh, Took, don't destroy that. Dude. I don't know what he wants, but I happened to notice that his water needed a refill while I was over there. Well, I don't think excuse me. I don't think I care that much about these parameters because they couldn't possibly be the gains I'm looking for at this point, but I'm kind of curious what they are. Where's Tuke? Oh, is he in the box? We should all watch him poop. We don't need to watch him poop. Be nice to know where these came from, though. So we do this thing 3 times. Oh, these are like separate flags for whether each axis has been something or other initialization processed yet. If I were to assume they are doing these axes in order, this would be the first one. 21. 21 and 20. And just 21. Huh. And what is this IMU table thing yet? Tuco does have an interesting litter box routine. Oh, we can see his eyes glow. Yeah, Bill says it needs to be armed with a water pistol. Yeah, that might be nice. Doing that 32 times. Is this a filter with a lot of iterations? I don't know why we'd be doing this so often. What algorithm could this be? We could actually put the base address in for that. Hey Tuke, I turned up the gain on the vertical axis and now it's oscillating too much. Just turn the gain down. This might just be like a longer term average of the related to the drift, but if that were the case, I would expect it to be, or to expect there to be some interaction between this and the command 4 calibration. Maybe that parameter is all we got. 62. I mean, I didn't see the oscillation at the lower levels, but maybe there's some gain parameter we can look for how the gain is converted from velocity to like a motor PWM value. How does that part happen? Bill's asking if 60 and 61 are interesting. Are 60 and 61 interesting? I don't think we know anything about 60 and 61. They're not that interesting to me because they're such round numbers. Like if they're gains, they probably wouldn't be something like 1,000. This is probably like a limit or something, or maybe a scale. It's like slightly interesting. We don't know anything about it yet. 60 and 61. Did you see those in the code somewhere? Oh, I don't see any cross-refs to these. So either nobody's using these or we have not found the references yet. So it's next to stuff that's in the IMU type specific initialization. It's possible that these are leftover parameters for a different type of IMU. I don't know. It is right next to that gain that we were interested in, isn't it? And this one was from time 4. ADC4, there it is. So we followed this directly from the gyro packet. It's only been transformed to be calibrated into degrees per second, that's all. We're multiplying that. What other unit conversion could this be? This is probably actually the gain. So this is param 62 times the gyro input multiplied multiply again by 10 for some reason, and then convert to integer. Oh man, I don't know what's wrong with me, but like cup of noodles is sounding really tasty right now. And then a lot of the rest of this seems to be around transformations, storing the results in these parameters that eventually end up in param9 locally, and then eventually in the other microcontrollers param9 via command 0 and command D. So yeah, I want params that are referenced by time for body. That would be interesting. Like 66 and 68, stuff in this range. There's another big swath of unused parameters here. What's around there? 2F through 46. Bunch of stuff. Looks like stuff that's been typed out, right? Like round numbers here. Not stuff that's been calibrated or otherwise decided on algorithmically. It doesn't seem to be referred to by the code right here. Where's Tuco? Oh, Tuco's on the table right here. Oh. Who's got time in floating point seconds? Am I missing something important in chat here? A time delay. Oh, you mean the... In main, it was multiplying a float by 1,000. Oh, that was a mouse. Oh gosh, why do cup noodles sound so tasty right now? In Maine. Oh yeah, these. For time? I mean, that would make 55 through 57 values in milliseconds. I can't think of anywhere that would make sense. Like, we've got these little numbers here. I think these are related to, like, angular rates or something. Oh, hey, Took. I don't know if we have a better gain. Like, maybe that's... I would have expected there to at least be some kind of programmable gain between the velocity and like the motor power stage, but maybe that's hard-coded. Oh, time to velocity scale. Param OB seems to be kind of complicated. Like, it's used as a scale in a bunch of places, and I don't know quite what it's for. Don't really want to change it right now. It'd be neat if I knew which parameter was just actually like a scale on the motor power level output. This is that mystery accumulator. Yeah, this is... Who else uses this? It sure does make it look like param B is a gain, doesn't it? Oh. Oh no, Tuco found the mice. His is a gain. We can test this actually. I think that might be it. Let's try that out. So if B is the gain, I need to bring the camera over here. So let's try a simple test here using these weird motor modes. So this will be using what we know about the weird motor modes in parameter 18. So I think this thing that we're looking at has to do with the velocity feedback loop. So I think this might have to do with the motor drive strength that we'll see in mode 3, which is the simplest velocity control mode. So we need another window where we can view the motor currents. Okay, velocities are 0. So I need to carefully put this into mode 3. So I should be able to apply velocity to the yaw axis. No? Oh, somebody turned off the motor. Might have to disable some of my safety features here. Oh yeah, it's not happy about that. What was that? Oh yeah, the peak detector. Let's temporarily make the peak detector not detect this condition. Well, maybe not. Maybe let's just do shorter tests. 50. It shouldn't have been applying that much torque. Yeah, let's try this one axis at a time. So those are off. Can we turn on the yaw axis in mode 3? Okay, I'm gonna use the controller to turn the gimbal back on. I think it's on. Oh yeah. Okay, so I can feel it pulling toward some position target which moves at this rate. And there's like a spring that's connected to a virtual object that's then moving at a rate. That makes sense. I want to see if I can adjust that effect by changing param. B. So that's 500. Whoa. Right. Let's try setting that to something really small first. Not 0. To 42. And this will still be something near 0. Let's turn the gimbal back on. I pressed the button. Oh yeah. It does feel like it's pressing less hard to try to maintain position. Maybe they didn't actually have to tune the velocity that much. Maybe the velocity, or that gain rather, for the velocity feedback loop. This doesn't seem to be powerful enough to actually move. Well, I guess one more experiment is I could see if this affects the stability in the regions I've been having trouble with. So for that, let's set this back where it was. Turn this back off for the moment. Ah, yeah. Be nice to have specific ranges that I can set for each of these controls. So I'll set it back to 500, same as factory. Motor modes right now are 0. So I'm about to set the motor modes back to 1, which should turn the gimbal back on. Hi, gimbal. Alright, let's try going low. So the first two axes are oscillating. That's yaw and roll. So yeah, I had adjusted the other thing that was kind of gain-like. Oh, it's oscillating a little bit right now, just not at the threshold. So I tried adjusting, oh, what was it called? 62. And that one was interesting. 62, you can definitely make it unstable by adjusting that. I didn't find a range there that was useful for this problem, though, which makes me think maybe it's the wrong control loop to be adjusting. So what happens if we make these lower? Here's yaw cut pretty much in half. Seems fine. And of course I'm not asking it to move very fast right now. I'm turning down roll. I'm hearing a little bit of audible vibration. Oh, if I poke roll, actually, it's very loose. It does settle back to the right location, but slowly. Interesting. Oh. Oh. My detector detected the error and shut it off. I'm gonna manually turn it back on. Huh. Oh. No signs of vibration at this angle. Hello, beer. Can we go lower? I think this might be the right parameter. Yeah, it gets down to there before being unstable at all. It's not bad. Bill's asking me why I haven't tried making it bigger. I don't think I need more energy in the system, which is what larger numbers would represent. I think that would make the vibration worse rather than better. I could try it, but like there's the fact that I don't think it would work, and then there's also the fact that it's like harder on the system and involves like more wear and tear on all the components. So like I don't think there's a good reason to go in that direction, and it just seems more likely to be a problem. We could try it, but I'm not quite into that right now. I'm more into stability instead of instability for this. This is much better. A little bit of instability right in there, but not very much, really. And that's still on the red and green. We could try going further. What is 90 degrees in this coordinate system? That would be, what, 1024? I guess I already had that set to the limit. Wow. That is pointed straight down. That limit's not bad. I mean, we can go up a little higher. I don't think we'd want it to necessarily be straight down. That's some interesting oscillation. Is my detector just too sensitive, maybe? It was audibly oscillating right there. It's interesting. Starts with, unsurprisingly, the roll axis again. It's not bad. This is a big improvement. Yeah, this is a big improvement. This is also probably not a bad place to try to compensate for changes due to power supply voltage if I wanted to do that kind of a thing. Oh, there's Tuco. Well, we could try sending this over to hang out with Tuco. Just like playing with it to test stability a little bit. It does wobble a little bit in the roll axis. So this is all just in RAM. I have not saved any of this into flash memory. There's a way to save it to flash memory in the gimbal. I'm also thinking about having a way of asking the config file to store some parameter overrides for the gimbal, which might be a good way to store stuff like this that we want easy access to. But that's not done yet. Right now it's all temporary. Let's see if we can get an overhead view of Tuco. That's what I wanted. Okay, so he's over there on the chair. He's still right over there next to the end stop, just the way I was driving it. Let's go over here. This will be nicer once I've got the controls in the camera's coordinate system. Oh man, the motion control right now is so bad. It's just like barely set up so that I can drive it at this point. It's not going to be smooth, and it certainly isn't. I think sometimes when the flyer is oscillating, it triggers my oscillation detector for the gimbal motors. Oh yeah, and then Neil is suggesting maybe those gains should change as the pose of the gimbal changes. Yeah, that's another reason for maybe them not to be just part of the flash memory config on the gimbal. But yeah, maybe we can change them dynamically too. Whoa, pardon the bad flying. It's really hard to fly in that corner. The tensions on the cords are really not what the bare bones motion controller expects them to be. Oh, he's like way in the corner on both axes in the gimbal right now. Oh man, there's so many bugs here. Come on, there we go. Well, regardless of the other bugs I'm hitting, at least I can aim further down, and I only sometimes hit the gimbal oscillation detector, which is what's happening here. Right there, it's happy for a little while. See, that's what happens when the oscillation detector just runs. If I let the oscillation detector and the computer vision fight, then we get the oscillation you were seeing. Like that. How bad is that on the graph? Neil is asking if my graphs include in the information I need to do like a step response test. Yeah, I mean, that's a good question. It's just that right now the problem I'm seeing is with a lot of layers stacked together, and I could try to test individual layers, but so far I haven't been able to reproduce the problem with just some of these layers. Like there are some diagnostic modes I can use to turn off the higher levels of the control, but so far I haven't been able to get the vibration with that simplified setup. It was stable for a bit when it was aimed straight down. So yeah, you can see the oscillation was building on, so the red and green traces are the yaw and roll motors. And then this reaches the threshold and we start trying to correct, and then the correction algorithm also oscillates, which is great. See, there's like a point of additional stability when it's aimed straight down, because the weight of the camera is balanced. I mean, we could try increasing the gains. Just to see what that would do. I mean, we've got these peak detectors already to see if we could try to keep that from being a problem. It looks like it's starting on the roll axis, so... Alright, that's a modest increase up to 600. Oh, and that just goes into oscillation right away. Oh, I can't actually aim to Tuco at this point. It starts oscillating away before we get to 2. About much less than that. Maybe like around 100-ish. That's kind of nice. Those currents on the roll motor are just really low now, relative to what they were. That is nice. I'm probably going to try to write something that saves these parameters. Yeah, it probably would be useful to have something that... I don't know, my inclination is to write something pretty generic, so I can just say, like, parameter B, set them to these values, and just have that in my robot configuration. I don't know. There are also advantages to just spelling out that these are the gains. But yeah, that's nice. That angle is so much deeper than what we've been getting before. You've got to see this on the DSLR. I should kill that light. Yeah, that's about what I had in mind. Overhead cat-on chair view. Oh, that seems like a decent spot to end today's stream at. It's 11 p.m. here, and seems like a decent time on a Friday night to wrap this up. But yeah, I think the next step here is probably just some more connecting the dots, kind of coding, getting stuff like this saved in the configuration file and then loaded like whenever it needs to be loaded. But look how much bigger our box is. That I guess it's over near the bottom of the screen. That box indicates where the gimbal can travel, and it is much taller now that we can move the gimbal down into that pointing down region without it being completely unstable. Well, thanks so much for joining today. Hope that was interesting, and let me know what you think. I'm on Twitter and the YouTube and Twitch, and let me know what you think in the comments and all that. But yeah, and I appreciate it when you hang out with the show and share it with your friends, and when you send in hardware, or when you chuck a couple of bucks my way every month on Patreon to help me keep this going. This show is funded pretty much entirely by viewers like you these days, so I'm going to keep trying to bring interesting content to the workbench, and I'll see you next time. Until then, happy hacking.